All right, so here we have a random variable I. It has two outcomes, 0 or 1, so we're looking at like categorical data. And let's suppose probability of getting a 1 is p, and the probability of getting a 0 is 1 minus p. So we've seen before, I'll run you through it again just because it's easy. The expected value of I is just going to be 0 times its probability plus 1 times the probability of getting 1, and that just boils down to p. But what if we want to do something like the expected value of 3i or 17.2i or ai for some real number a? What would that be? Well, what I can do is I can create a new probability distribution for ai. And what that does is that gives me two values, a times 0 and a times 1. Now, the probability of getting a 0 there is still 1 minus p. The a doesn't change that. The probability of getting a 1 there is still p. And notice that this is just 0, and that's a. So the probability of the expected value of ai is going to be, well, there are two values. You could get a 0. I want to do that in blue. You get a 0, and that was with the probability 1 minus p. Or you could get an a, and that happens with the probability p. And that just boils down to ap. In particular, it's a times the expected value of I. And this is super nice. Basically, it says that you can just factor out the a. So let's look at the variance of ai. Now that we know the expected value is ap, we can do this. So what do? We take the two different values, so it could be 0, and I subtract off the expected value, which is ap. And then I square it, and I multiply it by it times its probability. Plus, the other value is a, and I subtract off ap, and I square it, and I multiply it by its probability, which is p. And now I'm just going to calculate this. This gives me negative ap, and when I square that, the negative becomes a positive, and I get a squared p squared times 1 minus p plus, what I can do here is I can a times 1 minus p squared times p, and that's going to give me a squared p squared times 1 minus p plus a squared 1 minus p squared p. Oh, well, look at this. I can factor out an a squared out of both of them. And then out of what's remaining, I can factor out a p out of both of them. And that's going to leave me with a p there and nothing there. I can also factor out a 1 minus p out of both of them. And that leaves me with nothing there. And here I'm left with 1 minus p. And then notice p plus 1 minus p just gives me 1. So I end up with a squared times p times 1 minus p. And from our previous video, you know that p times 1 minus p is the variance. So I end up with a squared times v of I. So this is pretty nice. So maybe I'll write it here so it's a little bit neater. And that's equal to a. These are the two takeaways from the video. If I multiply all the outcomes by a certain number, the expected value just multiplies by that number too, and that's super nice. That's exactly what you'd hope for. The variance almost works out nicely. If you multiply all the outcomes by a, you can just pull the a out, but you have to square it. So that is not quite so nice, but it could be a lot worse. But I should also tell you that this this is good because you actually don't ever want a negative variance. Variance measures the spread and how spread out stuff is. And so you don't want things to be spread out a negative amount. So the math actually captures this in that now that since it's a squared, you can't have a negative times, say, a positive variance to get a negative variance just by multiplying by that. But this is how we deal with when you multiply by a scalar. Expected value works really nice. You can just pull the scalar out front. Variance works pretty nicely. You just pull the scalar out, but you have to square it. That is all. Thank you.